My name is Alejandro Falcón, CIBSE UAE Social Secretary and Events Organizer, and I welcome you today to our CIBSE UAE webinar, Understanding PICVs for Effective Flow Control in Variable Volume Systems. For those who don't know or not familiar with the region, our role here is to promote the intellectual welfare of its members, of system members, and improve the understanding of building services engineering within our society by organizing events and other activities related to the built environment. Today's agenda will be the speaker introduction, speaker's agenda, note of the session, a speaker presentation, there will be a Q&A session and a closeout. Our speakers today are Mark Walker, he's a technical specification manager of Hattersley. Mark has been with Hattersley for 12 years with diverse expertise in areas of variable flow systems. He has been involved in many projects over this time, covering applications such as data centers, district heating networks, clean rooms, commercial offices, and industrial processes. During his time with Hattersley, Mark has held different key positions, from internal technical sales engineer, external area sales manager, and specification engineer. Our speaker, Ahmad Marzouk, is a regional technical manager at Hattersley. Ahmad is a building services professional with diversified expertise in the area of building automation systems, HVAC systems, and fluid controls over the past 15 years. He held different key positions with leading corporates such as Honeywell, Siemens, Carrier, and currently with Hattersley as a regional technical manager. The technical agenda today will cover the following aspects: carbon emissions, assessment schemes and carbon net zero and energy consumption, basic concept of water system, why we need balancing in our systems, cost and flow system, what control where needed, the improvement to variable flow systems under control strategy, the need for pressure protection from modulating valves and dynamic speed pumps, pump infinity loss, overcompensation in system design for large temperature drops in the UK, introduction to PICVs, how they work, how they control fluctuating pressure, do's and don'ts of installing these valves, how to select these valves, type of actuators that come with these valves, end-of-line application. If you have questions, please kindly write them in the Q&A panel, and they will be answered at the end of the presentation in the Q&A panel by the speaker. Your camera will be off and your mic will be mute. Without further delay, I give way to the speakers of the day, Mark Walker and Ahmad Marzouk. Mark, the call is all yours.
Can you hear me now?
Yes, Mark. Can you please start?
My apologies on that.
Just go ahead.
My apologies on that. Thank you very much. Apologies from that. It was showing that I had a problem with my microphone, my end. So let me try this again. Basically, as we become more aware of the possible effects of global warming, the issues of reductions in the energy use, carbon footprint and CO2 emissions should be in the utmost of engineers' minds. This has led to the development of various assessment schemes And obviously, globally, building service industries is tackling the CO2 emission concern. We've obviously introduced BREEAM as being one of the first. That was introduced in around about 1990 and is used with over 50 countries worldwide. There are other assessments as well, like LEED and GBC, that are being used. So global energy itself, if we look at figures, around about 2017, there was 113,000 tons of kilowatts of hour of energy being consumed, and say 40% of that was being attributed to buildings. So 1 terawatt hour is equivalent to around about 5 billion barrels of oil. Or 1 billion tons of coal a year. So you can see, times it by 113,000, it's a humongous amount of resources, Earth resources, that are being used to create this global energy. If you look at the HVAC, 25% of global energy is attributed to the HVAC sector, and just by changing your pumps from constant to a variable flow, we seem to be looking at around about 6 to 8% of reduction in the energy consumption in the HVAC sector. So within this presentation, what I'll be doing is mostly looking at a schematic. It is going to be a very basic schematic, but you'll have a primary circuit, which has got primary pumps, low loss header, and then we've got 2 secondary circuits, each controlled by secondary pumps, 1 to do plant equipment and 1 to do fit out equipment. So firstly, we need to understand the nature of water. It's inherently lazy. It takes the path of least resistance. So unless we force it otherwise, we find that the equipment furthest from our pumps will get under pressure and starvation, and the equipment closest to the pumps will get overflow, overpressure, and therefore overperformance. So it means we have a natural unbalance within the system. This equates to an unbalanced system and a very inefficient system. So to counteract this, we can use regulating valves to balance the energy in the system. It's a method that we call proportional balancing, and we first came across this when we looked at constant flow systems. So basically, by installing and commissioning our DRVs, we can add resistance and redirect water to where we want it, overcoming this natural imbalance within the system. This was used, as I mentioned before, very much in the constant flow systems originally, and again, it causes a good balance within the system. However, it's still inefficient, and you still cannot control your terminal units, and especially the heat output from that. So what we would need to do is we firstly installed 3 or 4 port control valves and adding a bypass to these terminal units. This would allow water to obviously go 100% or full load through your coil, but also it allowed for a full bypass and modulating between the two. Whatever way you would look and the 3-port valve was operating, you would always use 100% of the energy, and thus remaining very inefficient in terms of energy use within the system. So how do we make it more energy efficient? Well, we would need to convert your system from a constant flow to a variable flow system. And this can be done by adding an inverter to the variable to the pumps to make it an variable speed pump. It allows us to change the energy that is supplied to the system in reaction to demand of that system. Our 3 or 4 port valves are now not really suitable and need to be changed. You can still have those, but they will be more on an end of line application where you're looking to pass back a minimum pump turn down. But effectively in a variable flow system, you'd be looking at a 2-port control valve. These would allow fluid through your terminal unit, or modulating between full and no flow, and therefore completely shutting off. when not required. Therefore, we can see an improvement with the energy usage. However, with this sort of modulation going on, we find that we introduce a natural imbalance within the system again. And it can be simply explained by, if we look at the system and look at, for instance, the secondary side with fit out side, where we have two circuits, you have a green and an orange. When all the 2-port control valves are fully open and you've got full demand of your system, you will never see any imbalance. Everything will be working correctly and you'll get the correct heat output to your terminal units. If, for instance, 2 of your 2-port control valves start to modulate close, what you will see is an increase in pressure and flow, not only to the remaining fan coil unit within that circuit, but elsewhere within the rest of that system. Therefore, we've introduced what we call a fluctuating differential pressure within this circuit. How? Well, as you can see, we've got an increase in pressure and flow at the moment. What I haven't shown, unfortunately, is the differential pressure sensors within the circuit. But if you can imagine, they'll be 2/3 up the run, say, for instance. These will detect the increase in pressure above the set point, and therefore will send a signal via the BMS to your pumps to basically ramp down and therefore drop your pressure within the system to the set parameters. Therefore, the increase in fluctuating increase in pressure and then the subsequent reduction in pressure from your pumps causes this differential fluctuation. What happens? Well, in that time of the fluctuating pressures, what you'll find is you will lose your control valve authority. So therefore, what we would tend to do in the old days of variable flow would be to introduce valves like DPCVs and companion valves. These would be put into the system, usually in more than one location, and you would find with these type of valves, the size and groupings and number of valves, number of units within the groupings was fairly critical. However, in simple terms, the differential pressure control valve, or DPCV, protects the system from differential fluctuating pressures and creates a stable or known environment for the circuit that it is protecting. The control valve authority, should I say, is an important aspect here. I will be discussing it in a few more slides later on, but by creating a stable environment, we can control and improve control valve authority. That's the critical point about making your building system efficient. So by introducing these type of valves, you get a balanced system and a very efficient system. So control valve authority, as I just mentioned before, is the relationship between your control valve and heat output. By having a good control valve authority, we have a good control of our heat output, utilizing various control methods. But the calculation is fairly simple. It's basically your delta P across your 2-port against your delta P across your circuit. And that will give you a number up to a maximum of 1. So if we have a look at a basic DPCV system, just for a basic principle, so you can see how these type of valves can influence valve authority. We have a typical branch which has got an 80 kPa head available for this particular circuit on the example. Your control valve has a 20 kPa loss across the 2-port control valve. Therefore, if we do the maths of your 2-port loss against your circuit loss, you get 20 divided by 80. That will give you a 0.25 valve authority. We know that CIBSE's guidelines means that we have a recommendation of a minimum authority of 0.5. Therefore, this example does not achieve the acceptable authority. We have to do something to make sure that we have that good valve authority. In this case, we would install a DPCV and a companion valve. The DPCV is set to control at design flow rate. So in the example where we have in the location, your 2-port control valve again will still be dropping 20 kPa at design flow rate, but because the location of your DPCV, you'll be setting that with the pipe losses and the obviously the coil losses and your valve losses will be set to around about 40 kPa. Therefore, when we do the maths, 20 divided by 40, we do get the acceptable minimum level of authority, which is 0.5. If we were to, for instance, change the location of the DPCV and bring it closer to a single terminal unit on a branch, and then we will redo the calculation. For instance, we have a 20 kPa loss on the control valve again, but because we've only got a smaller pipework arrangement and we've only got the coil of the terminal unit to also take into consideration, the DPCV setting is much closer to that 2-port control valve loss. Therefore, when we do the maths, we get a 0.8 valve authority. So again, the size of a circuit on the DPCV does also affect your valve authority. So it's something to take into consideration when you're looking at various different valves that you're putting on a variable flow system. DPCVs, like the PICVs I will be going on to in a few moments, there are do's and don'ts. The first one is you cannot really put DPCVs in series. These will hunt each other and you'll get oscillations between the two DPCVs. Also, with which you occasionally see, DPCVs, because of their control range, shall we say, they don't really need to be combined with any equipment that's being controlled by a PICV. The DPCV will be trying to create a glass ceiling of pressure, and therefore not utilising the PICV's fullest potential. So you can, in this scenario, remove the DPCV and companion valve because these PICVs are quite capable of going up to around about 800 kPa in terms of differential pressure and being able to control it. So if you do see this scenario, then the DPCV and companion valve is not really required. Also, one thing to just bear in your mind is if this is incorrectly set, then it will have a big bearing on these PICV performances. So going back to the DPCVs and being installed within the system, as you can see, by changing the size of the circuit, it does affect the valve authority. Therefore, how can we improve the efficiency of these types of systems? Well, we can install a PICV, a pressure independent control valve. This replaces a 2-port control valve, which modulates our flow rate, the double regulation valve or commissioning set, which balances our flow rate, and the DPCV, which manages our pressures. Now, as you can see in the DPCV type variable flow system, it's quite cluttered. You've got a large number of valves there. It takes a little while to obviously for the labour to install these and also to commission these. So by removing all these valves, as you can see, and installing a PICV in its place, the system becomes a lot neater in terms of the amount of valves that you've got to install, as well as the commissioning and labour content in terms of installing this type of system. I will just say this is a very, very basic system. The PICVs themselves, they don't have the facility of isolation. So you would still need to have isolation on your flow and return, and also on your flushing bypass, for instance, for each of these terminal units. The pressure tappings either side of the valve is not for flow regulation on this type of unit. It's really there to ensure that you have the correct pressure in terms of activation of these PICVs. And we'll talk about that with a practical demonstration by my colleague in a few minutes. But by introducing the PICV, you've got a much better balanced system, and it becomes a much more efficient system. So just before I go any further, I will just mention about the Kirchhoff's second law, which we use when we're looking at variable and constant flow systems, and the reasons why you don't need to use this type of scenario when you come to PICVs. Firstly, his second law states that the total head loss in parallel path or each parallel path caused by flowing of fluids must be equal. So by applying this law, we know that regardless of the path taken, the pressure drop between point A, which is the impulse tube connection on this example, and B will always be the same, which is the DPCV. So from the path of point A through coil 1 to point B will be exactly the same as from A through coil 2 to B, and therefore through A coil or terminal unit coil 3 to B. Although the flow rates may be different and the control valve pressure drops may also differ, each of the circuits, the total pressure drop through these circuits must be the same. Therefore, by installing our balancing valve and the pressure drops and consequently the percentage of design flow rates can be balanced against each other. So this also happens within the DPCV system as well as the constant flow system, and therefore with commissioning of these type of systems you need to allow for obviously proportional balancing, which this basically is. So just to recap, going from a constant to a variable flow system, obviously we lose this stability within the system itself. However, with the correct control strategy, we can see potentials for large energy savings. And what I mean by that is, if I take, for instance, countries which have got seasonal variations, say for instance the UK, the temperatures can vary massively from month to month, season to season, and increasing year to year. Due to this, we often see that some of the systems are oversized to compensate for the large variations. So typically in the UK, you may have 70% of your cooling season loads less than 50%. But equating that to energy consumption, if we have pumps running at 50%, our flow rate is reduced. It's a direct relationship to 50%. There are squared and cube relationships. So if we run our pump speed and therefore our flow rate at 50%, we only have to use a quarter, or we only find there's a quarter of the resistance within the circuit. There is a cube relationship, which is power. So therefore, if we're running our pumps at 50%, we only need to use 1/8 of the energy. So therefore, we can see large potentials of energy savings. However, I will just mention that obviously various different companies do have different efficiencies in their pumps. But one thing we do know is that by reducing our pump speed, we can get energy savings of circa around about 70%. But when you are considering reducing your power and obviously your pump speed, you also reduce the efficiency of your pumps, and therefore any energy savings must be offset against your highest and lowest efficiencies of your pumps. So hopefully that gives you a quick overview of your variable flow, constant flow, and some of the valves that you associate inside these type of systems, as well as a potential for seeing these energy savings. What I'll do now is I'll just quickly talk about the PICV itself, which is the main context of the presentation. So as I've already mentioned, with a DPCV system on the variable flow, you had large cluttered amount of valves within the system. By introducing your PICV, you won't have to install a DPCV. Your companion valve, the commissioning valves like DRVs and commissioning sets, and also the 2-port control valves, which makes installation a lot quicker. However, with a PICV, as I mentioned before, there sometimes isn't any flow verification devices on it. So you would need to add a flow measurement device, and I suggest that you do it locally. If it was, for instance, on a branch where you have a number of terminal units, you would have to do a deduction method to make sure and ensure that you have the correct flow rates set up on each of these PICVs. So having the local flow measurement device on, say, for instance, the flow or the return that's close coupled to a PICV would greatly increase the speed in which you can commission your PICVs. I will just add on the branches, because you've had the PICVs, which I will come on against or coming to a little bit later on, but because they have a differential pressure controller inside them, and you have this facility of measuring flow rate, you wouldn't really need to have commissioning sets on your branches. You could just have IVs and maybe an orifice plate or some sort of flow measurement device, just so that you can verify flow rate going onto maybe a floor or for a zone for where you've got fan cool units, chill beams, or air handling units, for instance. So the pressure independent control valve itself has various features. First one being flow regulation. As you can see, by adjusting the dial, what happens is it changes the open space between the seat and disc, and therefore it changes the gap to which the water flows. The pressure across the seat and disc is held constant by a differential pressure controller. So whilst setting the open area around the disc will result in changing of the flow rate. The DPCV, or should I say the differential pressure controller, then recreates that constant seat differential pressure, and therefore setting a new flow rate that will stay constant at the new valve setting. Flow modulation, which basically it takes the part of the 2-port control valve. With this example, what it's going to be showing you is a room temperature thermostat is picking up that the room temperature is above set point. It will send a BMS signal to the actuator to say that it needs to drive open and therefore reduce the temperature within the room. So as you can see, by using the PICV as a 2-port control valve, it allows the variation of flow rate to vary the heat output of your terminal unit. So as the stem withdraws, it increases the flow, and therefore your cooling output of your terminal unit, once it's got to the set position, it will then send that seat back to the set position on your PICV. So some PICVs come with equal percentage, some are linear controlled, which I'll talk about in a little while, but basically, effectively, your actuator will then be doing your heat output curves. The third function of a PICV is basically a differential pressure controller. So in this example, you can see that there's an increase in pump head. This is counteracted by your bottom stem. It's exactly the same as what you'd see in a PICV. So you would have an impulse tube which transmits your flow pressure or inlet pressure to your bottom chamber, and then the water pressure coming off of that gap between the seat and disc is then collected within the actual hollow stem itself. Therefore, because you have got the two water pressures, because we have basically a set differential that this valve tries to hold against in this on this gap, it will then obviously vary your stem, etc., to keep that differential pressure constant and therefore constant flow rate with the stem in the same position. We'll just run it again because I think it's quite low in terms of what you can see, but you can see the bottom stem actually rising when there is an increase in pressure to maintain that set differential across that gap. And then as your pressure or your pumps reduce, then basically your stem will withdraw again, allowing more or recreating that set pressure again and maintaining that flow rate. So PICVs themselves, they can be installed in various locations and various pieces of equipment, from chill beams to heat interface units. One thing I will just mention here is PICVs in terms of radiator circuits and underfloor heating circuits are not really suitable, especially if it's a traditional TRV head and knock shield valve. What happens is the PICVs and the TRVs will fight each other. The TRVs will obviously get to room temperature and start closing, and the PICV will try to maintain a constant flow to that area. So therefore we have that obviously hunting between the two valves. With the underfloor heating circuits, again, they're usually pumped. They usually, if they're not, they usually have some sort of two-port control valve or TRV modulation on those type of manifolds themselves. So therefore a DPCV is probably a little more suitable for both applications. So I mentioned about valve authority earlier and in terms of a DPCV. Now with a PICV, as I mentioned before, the circuit is only the gap between the seat and disc. So therefore, when we looked at the previous example, we had a single terminal unit with a DPCV, a companion valve, which you can see here, a two-port control valve and the commissioning set, plus the loss in the pipework and the coil, would give you around about 0.8 authority. But if we then replace all those valves with a PICV, because the circuit is so small and it's integral to the valve body itself, the valve authority at all settings is 1. So you can see you have a much vaster, efficient valve, and therefore you've got a much more efficient system that these valves basically can then be controlling your circuits with. And if you have a much more efficient system, then therefore you're using less energy. With PICVs themselves, they can be put on the flow and return. As you noticed on all of these schematics, most of mine have been put on the return. It's only because any pipe work before the PICV has the highest system pressure available at that location. Anything after the PICV has lower system pressure. So therefore, and bearing in mind the PICV is quite a high loss valve itself, there is a chance that your coils could have cavitation forming. So having the PICV on the return just helps that. It's good. It's better practice to do it that way. Also, clear straight lengths of pipe work are not really required in front of a PICV. However, find it is good practice to allow some straight lengths of pipe work. So for instance, if you're directly connecting this to the, for instance, a fan coil unit that has copper tails on it, having that connected directly on it, you should have enough straight lengths in there so that you have a more suitable flow pattern of water within your pipework. Again, having a 90-degree bend to it, again, makes you having eddies and more unstable flow pattern entering the PICV. So obviously, small amount of diameters of pipework is a better and good practice for installing your PICVs. The PICV, as I mentioned before, is a high loss valve, or can be a high loss valve. So in terms of flushing as well, if for instance you have like this example here, a single PICV, having them installed on unions is probably a little bit more advantageous because you can remove the PICV and replace it with a spool piece. Therefore, when you do your flushing, you'll be using less energy on your pumps because you won't be fighting against these high loss valves like a DPCV, like a PICV, and especially with control valves as well. So a case of when you have loose PICVs, having them on unions is one alternative. You can leave them in situ when you do your flushing, but again, because you could have it, for instance, if you're doing a refurbishment system where you're connecting to an existing system, it could be quite an old system. So again, you've got the potential of water quality. So if you are flushing and then reintroducing it to an older system, you could potentially cause blockages, especially within the impulse tube area or that drilling. The drilling itself is only around about 3 millimeters in diameter. So again, there is the possibility of fine particles building up and blocking within that. You've got to remember, with the bottom and the top chambers within the DPCV differential pressure controller, there won't be any flow. Once it's filled, then basically there's no water flow. So again, you could get particles forming inside those impulse tube connections and blocking it, and therefore reducing the pressure transmission to your chambers and effectively reducing the performance of your PICV. So like with DPCVs and PICVs, we have a activation limit. With a PICV, we have a minimum and maximum. So for instance, we know that as water flows and increases, you get an increase in your differential pressure. There is as I mentioned before, there is a minimum and maximum. So as the flow increases, it reaches the activation point and the pressure controller starts to hold the differential seat pressure constant. At that point, between your minimum pressure and maximum pressure, which can be either 400 or 800 kPa within PICVs, it depends on the spring control range. We can offer both, but basically within that minimum and maximum activation limit, then flow rate is controlled, and therefore you'll have constant flow rate. After such maximum differential has been reached, what you'll find is the flow rate will continue to rise and the valve can no longer control the pressure. So you'll also see that differential pressure rise as well over those test points. Fundamentally, to have that happen, you would have to have at least 800 kPa pump differential for this to happen. So again, size of the system that you'll be working on, you just need to make sure that you have the correct PICV spring range for your application. As I mentioned before, with the PICV activation, the differential pressure can be measured using the test points applied. So the red one, which is always on the inlet connection side, is the high pressure side. The blue tagged test point is basically on the low pressure side or the outlet side of the valve. This should always be installed in this way round. You will see there is a flow indicator on the side of the body that ensures that the water flow is in the correct direction through the valve. So flow rate itself can't really be measured by these test points, and I will just explain that a little bit when we look at the next chart, which will be the flow settings and the flow rates. But basically, to get a more accurate and you won't have an inferred flow, you would have an actual reading, like CIBSE's guidelines, that you should have a verifiable, accurate way of measuring flow rate. So therefore, we always recommend having a FMD, a flow measurement device, an orifice plate, venturi, local to your PICV, so you can set that valve more accurately. The more accurate you can set it, better and more efficient your system. So we publish charts, DM15 low flow, for instance, standard flow and a high flow. As you can see on here, the PICVs usually have a minimum limit, and we usually say most PICVs on the market have a minimum limit of around about setting 2. They do go on to 100% open, which is setting 10. Against each one of those set points, you see a flow rate and a minimum activation. So that's 15 kPa, all the way up to setting 5. Then you usually see around about 20 kPa for further settings. You see, as you go up on your settings and your valves, also your minimum activation can increase. So it's something that you need to be wary of when you are installing, when you're commissioning, and when you're checking your pump sizes. What I'll do now is I'll hand that over to my colleague, Ahmad, and basically at the Flow Technology Center in Dubai. Ahmad, are you here?
Yes, Mark. Thank you so much for the nice presentation, and good evening, everyone. Actually, I'm going to, for a change, I'm going to go live and to show you our new Flow Technology Center from inside. So hi again. Actually, it's really interesting time as we are talking to industry professionals, and we have just started our new Flow Technology Center here in Dubai. It's a unique experience, and actually we can't wait to have you visiting in person in order to enjoy a really unique experience. For the time limitations, we won't be able to elaborate a lot about the facility and what it can offer, but I'm going to give you a short overview. Actually, it's the first facility within the region that employs a complete chilled water system, and that is only for experimental training and R&D purposes. We usually see products, maybe some demo kits or demo panels to simulate operation and functionality of products within this industry and specific chilled water systems. But what we have here is really different. We do have a complete and fully integrated chilled water system, which is put for these reasons. So just to brief you about the inclusions of this setup, we do have a chiller, we do have a fresh air handling unit and 9 tank coil units with the complete chilled water system, instruments and products, from valves to regulation to water quality maintenance products, as well as metering, sensing, and automation in the background. What you can see behind me here is a BMS screen, which is actually responsible for automating the whole setup. So everything can be controlled and monitored from the workstation, which is the BMS workstation. Likewise, collecting data, gathering data, analyzing the data, and conducting comparisons, validating theories, and testing assumptions within the industry is also possible within this facility. What I'm going to do now, actually, I'm going to shift the view in order to introduce a very short demo on one of the topics that my colleague Mark has mentioned a while ago, which is basically the correlation between the activation pressure and the flow regulation ability of the PICV. So basically what you see now on this view is a pump which is driving the flow of the water from the supply line, a return section which is equipped with a PICV, the N25 high flow version, a side flow glass which is a visual proof of the flow, and there are many more items within the circuit which are available for temperature measurement, pressure measurement, as well as different provisions for flow rate verification, such like the FMD. Our concern here is to have a look at the differential pressure across the PICV and the measured flow rate according to the data sheets. As Mark mentioned, the selection of the PICV is actually around the flow rate requirement of the coils. So if the selection is wrong, for instance, if it is oversized, which is actually a practice that we still see in the market and we can still see in the projects, you will end up with a deflection within the differential pressure, and that is going to impact the flow rate quality. Now for this PICV, we have a sitting dial, as you can see here, and we have removed the actuator just to be able to demonstrate this experiment. So the sitting dial is actually a very simple tool that by your fingers, you can just select the position of the sitting or the PICV sitting, according to which the flow rate, the corresponding flow rate should be delivered and maintained within the PICV. The color coding, as Mark mentioned, the high pressure, the low pressure. So we have the red upside and we have the blue downside. Those tubes are basically connected to a digital manometer, which is actually responsible for measuring the differential pressure across the PICV. And we are going to verify this in a moment. So what I have at present is a sitting at number 4, which should correspond to 0.36 liters per second for this specific size. That is providing the minimum activation pressure is available for the PICV in order for the differential pressure controller to engage. And for this position, it is 30 kPa. So we need to have 30 kPa at least in order to have the flow rate within the right range. I'm going to show you what's the differential pressure reading at present. I hope you can see the reading, which is 43 kPa, and that is the upper line. And that corresponds to a measured flow rate of 0.36 liters per second shown on the BTU meter right underneath the flow glass. Now we will take it to another level of sitting, which is position 6. So it's just basically moving the dial to number 6. And again, we need to verify the differential pressure at this position as measured, and what's the flow rate, and what is the correlation. So at this set, we should have 0.57 liters per second, providing that minimum of 38 kPa is developed across the PICV ports. Now, what we can read on the BTU meter is basically around 0.45 liters per second compared to 0.57. And that is basically due to deficiency in the differential pressure measured at this position. We can see here 25 kPa compared to a requirement of 38 kPa. This example is an actual example, and it really bothers a lot of installers because of something that they do miss during the commissioning. And it directly relates to the pump sizing, the head sizing and basically the pump curve selection. So we need to make sure that the differential pressure, the minimum requirement of differential pressure across the PICV is met in order to maintain the regulation ability of the PICV for the set position. And actually this PICV has been intentionally selected and installed within the pipework as oversized in order to be able to demonstrate this example. Many more examples and demonstrations can be done within the facility. That involves industry problems and breakthroughs and approaches towards R&D and a lot more. For that, we will be really honored to host you in person whenever your time permits, and as we are available and ready to host visitors in this facility. With that, I would like to thank you for listening and for your attendance to my part. And I will give the control back to Mark to continue. So thank you again.
Thank you, Ahmad. That was a fantastic demonstration there. As you can see on the screen, from that demonstration, you can see the two set points that my colleague used, which was setting 4 and setting 6. That's the typical differential pressure, which is the minimum activation and therefore the flow rate. So if we move on to the pump graph, what you would see is the setting 4 position here, which is equivalent to 1,312 litres an hour, and minimum requirement of your KPA. And as you can see, with enough pump pressure, it keeps the flow constant. And then this is the adjustment up to the setting 6, which is 1,621 litres an hour or 0.45 litres a second. And if you have enough pump pressure, what you would see is that the valve will hold that flow rate constant. If you had, and as it was shown, not enough pump pressure, and you have modulation within the system, you would see a fluctuation in your flow rate until such time that they had enough pump pressure or pump head to maintain a flow rate within that system, and then it will just drop again to a lower flow rate. So it's critical, as was being mentioned, that you do have enough pump pressure for your PICVs within the system. Also applies to having the correct differential pressure sensors set correctly, and that you have the correct end of line valves within the variable flows set 100% correctly as well. So as I mentioned before, the pressure losses can be read between the red and blue valves, test points on the valve itself. Critically, when we commission, we need to scan the entire system. We need to add those results to your flow charts and obviously the commissioning report. And then the presumption, the assumption should be not only that you scan the reference points and the index, but as you work closer towards the pumps, you should see higher pressures. And therefore, if all your PICVs are satisfied and see above the minimum activation, you shouldn't have any problems with the PICVs actually performing how they are intended to perform. Couple of things to note is PICVs come in various different control characteristics. We have on the market equal percentage, and we have linear control type PICVs. These work in different ways. With a equal percentage, the valve position equates to a heat output. It has that relationship, and therefore it's a little bit more complicated internals. And the actuator is a little bit more simplistic. and what that does is it drives down the linear combined line. The design of the actual plug is supposed to give you 100% open gap all the time. If, for instance, there is a slight change in loading, partial loadings, there can be a slight distortion if that gap distance does change, and therefore you could get a slight undermining in the valve authority. The other type of PICV is what we class as a linear control characteristic. It works slightly differently. It has a valve set position to a flow rate. It's a little bit more mechanically simplistic inside the valve. However, the actuators have got to be a little bit more intelligent. It can't just be a standard actuator on these type of valves. What happens with the linear is usually you have a change in stroke length as you change the dial at the top of the PICV to change your flow rate, which means that you have a drop in your stroke lengths. Therefore, your actuator should come with a gap detection. Therefore, it stops any dead cycle times and obviously improves the efficiency of the PICV itself in terms of regulating your flows. The design of the disc and seat meant that it's going to be adjustable for part loads as well. And as I've mentioned, there are various different actuators that come with the PICVs. And what I generally say is if you're looking at a manufacturer for a PICV, you should use the same actuator. They're designed to work together. Sometimes crossing over different manufacturer actuators with different PICVs, you can get around the complication of maybe not having the correct clearance for the top of the stroke. So therefore you get a slight compression. If you do get a compression on your stem, it could undermine the performance of your PICV if it's at almost high at the maximum flow rate. Other things are maybe fitments not 100% correct, so it might not have enough stroke. Just things like that needs to be reviewed before the PICV and the actuator is procured. But however, with modulating valves, usually it modulates the stem position between set point and the closed position. Usually they're available with gap detection. You could have feedback, and you also have ones with fail-safe open and closed. So it depends on the type of system that you're designed for and the type of control that you need on your actuators. Typically, some modulating valves come with dim switches, which can save time in terms of if you need to change the type of control from factory setting. Usually it's an equal percentage, usually it's a 0 volt equal fully open, say for instance, but you can change them around using those dim switches. There are other actuations, other actuators available, but bearing in mind some of these take different times in which to do a full stroke. So for instance, you could have a modulating valve that takes 8 seconds per millimeter, but you may have a 3-point or even a thermal actuator. Again, the times change per millimeter. So it's just something that you need to bear in mind in terms of how critical your control needs to be on your PICV. So where else can we use PICVs? I did mention beforehand 4 ports and end of line. So for instance, your terminal units, you could have a PICV on there, but because it's probably end of line, you need to consider within your design minimum pump turn down for your pumps. You may want to also look at circulation of your inhibitors or water treatment within the building itself. Having large dead legs means that you're not going to be circulating treatment all the way through. And also it's response time for your heating and your chilled services. Having an end of line on, say for instance, per floor can obviously help you in terms of circulation of that hot water or that chilled water, and therefore your terminal units which are branched off of that gets quicker temperatures, response times to what's demanded at that location. So just to recap, by using the PICV, we can remove the DPCV, the companion valve, commissioning sets, two-port control valves, etc. This does save time. As I've mentioned before with the valve authority, because obviously your valve authority with PICV is 1, and because it's a self-regulating valve, therefore we can cut down commissioning times as well, because each valve can be basically set and then basically forgotten. It just needs the activator put on there and energized for it to then start modulating. But effectively, as soon as you've scanned it, and if you've got enough pump pressure throughout your system, these valves will be able to perform to what your designs have been intended for them. So again, it also removes that proportional balancing of the systems, which increases commissioning or reduces commissioning times for your variable flow systems. There are other ways of increasing your efficiency of your installation. Sometimes you can find various manufacturers will be able to provide a PICV on a prefabricated arrangement. So for instance, on here, this one's a hookup. It will have an H body, so you can isolate your system side water, bypass, and this will be where your fan coil unit will be directly mounted to. PICV, you've got a flow measurement and you've got some sort of flushing for back flushing or back flushing of your coils. You've got various different test points which can do various items like checking your minimum activation and you've got enough pump pressure within your system, checking your flow rate, and the combination of several test points like the blue and the red here can then give you the DP across your coil as well, so you can see if there's no blockages. But as I say, there are various different variances on the market. These all have different variants within the product ranges as well, but again, it's just something that you can speed up the installation of your building and projects. That's so for instance, this one which is being shown here is just solely for fan coil units. They're designed to go over drip trays, therefore they don't need to be insulated. We do there are other variances on the market. This one's an 80mm wide chassis, so these are usually what we class as remote mounted. They're designed to be fitted to terminal units, but with flexes. It could go onto radiant panels, small air handling units, overdoor heaters. Again, PICV controlled, so you've got high efficiency. Strainers, H-body for isolation and flushing bypasses on your system side. But again, because these are slightly wider and they are remote, they are designed to go into ceiling voids or floor voids so that you can insulate both your flow and return pipework. So various different combinations. There are also ones which have typical commissioning sets on there, and that will basically be used within a DPCV system, controlled system. So again, 2 fan coil units, radiant panels, but being controlled by a DPCV. So what you would have is a 2-port control somewhere close to the terminal unit itself. So that really brings up and rounds up the PICV element. And as I say, hopefully you've enjoyed the presentation. I will be stopping now and sending that back to our main host, CIBSE host, and basically for questions, any questions from you guys.
Thank you very much, Mark. It has been a very good presentation, very insightful, very informative and instrumental to our engineering community really. Since definitely all we should design to maximize energy savings by doing so, releasing low carbon achieving low carbon emissions in the designs and projects that we do. This presentation really has been particularly special with the interactive virtual walkthrough through your facility. So thank you very much for that. And yeah, let's just get some questions from the audience that they have been writing from the beginning of the session. So if you can kindly answer them. So first question that we have from the beginning of the session is from Mohammed Irfan. Do we actually need a three-way control valves at the remote terminal units?
I can take this one. Yes and no. It depends on the terminal units themselves. If you are looking to have or incorporate a minimum pump turn down within your building or a floor, then yes, you could possibly put one on your terminal units. Otherwise, if you've got just a PICV and it's to do a normal operation, then no, it won't need to have a 3-port control valve on there. It's only for end-of-line applications. It's one option. You could have a PICV, say for instance, on a loop on the end of the pipework, and therefore it would become a constant flow device. You could always put an actuator on it, link it to the BMS so that if a certain percentage of your valves are closed, then that can then open. So you're ensuring that you're not adding to your design flow rate, but you have got enough. For instance, if for instance your pumps go down to a limited hertz, then the BMS will open that up to ensure that you've got circulation when it's got to that low demand set point. So there's various different ways of doing it, but no, fundamentally, when you look at when you're looking at terminal unit, you will not need to have a 3-port control valve. Okay,
thank you for that.
No problem.
Next question. Again, I'm reading a series. Came from Mohammed Irfan. He asked, do we need to verify the flow in each fan coil unit, or differential pressure verification itself is enough?
Usually, I would say yes. CIBSE tend to want to see that you've got flow verifications, obviously witnessing from your client. So having a flow measurement device and being able to measure each of your fan coil units, you can tell if you've got any blocked, if you've got any problems within the system. And it just helps with commissioning and setting up of your PICVs. If you, as I mentioned before, and as you can see from the flow charts, setting set points on, say for instance, between 2 and 4 on a 15mm low flow have more or less the same minimum activation. Your test points on your PICV will only indicate that you have between minimum activation and maximum activation. So theoretically, you may see 15 kPa, or you may see 300 kPa across those test points. It depends on where it's located and the amount of pressure that PICV is absorbing to provide that constant designed flow rate. So I would always say yes, have a flow measurement device and not rely on the inferred pressure drop across those test points.
Thank you for that. Thank you, Sorry. Right, so moving forward, Mohammed Masihuddin asked, does PSC valve, well, I think what he's trying to say is, are PSC valves leakage proof?
Leak proof. No, they will always have some sort of, although they will close, they do have a leak class. I think it's between 3 and 5 or 3 and 4, depending on the type of and size of the PICV. But they should never be used as isolation. They will have a slight leakage to it, but again, it's absolute minimal. But it needs to be understood that yes, it will close, but there will be a slight trickle after a while.
Thank you. So Mohammed Irfan asks us, some of the PICV manufacturers does not have the option to measure the differential pressure, as the provided ports are not upstream or downstream, especially for a smaller size valve. What they say is they will verify the flow rate only. Does that make sense?
Sorry, could you say that again? It was I couldn't quite hear that last one.
Yeah, seems that the question is some of the PICV manufacturers don't have the option to measure the differential pressure at the provided port, or as the provided ports are not upstream or downstream, especially for the smaller size valves. What they say is they will verify the flow rate only. Doesn't make sense. I think aligns also with the previous question on differential pressure, but please, if you can clarify this question for him.
Sometimes, as you rightly say, it may not do it. It may only do it over the differential pressure controller. It does depend on various different manufacturers. But again, you have an inferred flow. If somebody asks you, okay, can you prove it? I would always suggest having a flow measurement device locally. You could have it on the branch, as I mentioned before, as long as it's sensitive enough to measure the drops between your various different terminal units. So therefore you can do a deduction method in terms of the drops of the signal would then be able to be equated back to a flow rate. It's always a difficult one. Some manufacturers do provide test points, do produce flow charts and things like that against the pressure, but again, it's always the same. Are they accurate, and can you verify 100% that that is accurate? Flow measurement devices are always probably the most accurate way of measuring flow, so I would always suggest having something incorporated in the system.
Definitely. All right, thank you. Next question is from Ali Azar. He asked us, could you please elaborate on the testing method for PICVs to ensure EQM characteristics are inherent of the valve, independent of the actuator? For example, EQM is not imitated using the actuator. If you can respond to that. I'm not expecting you to elaborate completely again the whole thing, but if you can just perhaps give a quick brief high level for him.
Yeah, basically with the PICV, it's sorry, I missed. Do you have the question? I was just trying to have a look at it in terms of how to respond to that. I might. Is it possible to come back to that one so I can have a think about that one?
Yeah, no problem. Let's just continue. So Syed Hussein is asking us, what is the accuracy of H&H PICV on the bronze range and large diameter ferrous ones? Whether that is something you have on top of your mind, otherwise I can continue with the question.
Accuracy, it's around about plus or minus 10%, I believe, on some of the valves. With the larger valves, I think they're more or less plus or minus 10 to plus or minus 15. It does depend on the size. Some of them alter within that the bronze range as well, but generally they're between plus or minus 10 and plus or minus 15 worst case scenarios.
Thank you for that. That's some of the questions over here. For large networks, for example, in a campus, you have a centralized pumping system and you have long networks. What would you say, what are your thoughts on lack of or loss of precision of the PIC valves in terms of controls? Do they lose performance due to long or large 2-watt distribution networks?
I have seen usually the only thing I've seen on that is on ultra low flow rates, where you've got tolerances, and bear in mind you're talking about the absolute minimum is like down to 0.006, 0.008. You can see those shifting slightly. It's something that a lot of consultants in the UK are starting to recognise. So they are designing their flow rates to be around about 0.02 litres a second, 0.016, around about that size, and it seems to, and that happens to quite a lot of the PICVs on the market. So they are sort of putting a limit on how low the PICVs are going, and that makes sure that you've got good repeatability and good accuracy, and it seems to be working quite well with the PICVs, and that's from various different sites in the UK that I've seen, with various different manufacturers as well. So it seems to be applying to virtually all the PICVs.
Thank you for that.
No problem.
There is since there's here a typical question that many ask. So what are your thoughts on the following? There are many opinions that the PSC valve should be set in factory and then brought to site, or other people think that the PSC valve should be brought to site, and only once they are installed in the right place, they are set so that there is no risk of mixing valves and putting them in the wrong position, in the wrong place. What are your thoughts about this?
It's an interesting one. It's I've had that asked several times. I look at it in several ways. Yes, that is one of the reasons. With loose valves, they can be put in the wrong position, and therefore you would need to still commission again. Usually when you do commissioning, you scan the area and you would check all your flow rates, and the valves have to be fully open. So if they were preset for commissioning purposes, they should be fully open. It's one of the first steps that they need to happen with a system, just to make sure that they've got no blockages, that you've got no problems within the system itself. The second reason is the PICV itself. Yes, you have got a percentage performance. So we, or a manufacturer, shall I say, could set it to, say for instance, setting 3. But when it gets to site, you could, or you may need to just alter that a fraction. Again, it could be to do with repeatability. It could be to do with the being slightly moved in transit, vibrations, etc. Or it could be that, as I say, you've got slight manufacturing tolerances. So again, you may need to just fractionally move it. So I would always say, yes, there is that possibility. We tend to send them out because we test every single one before it goes out. So usually it arrives to site fully open. So it's just a case of closing it and then reopening it. There is always that problem as well. All PICVs and most other balancing valves should be set in a certain way, either on rising pressure or lowering pressure. So having something set in the factory, somebody may, for instance, just tweak it from closed position to the set point and leave it like that. Another operator may take it further past and then backing it back up, so it's on rising pressure. So you do get a very, and I mean very, very slight differences in terms of how they set those PICVs up. But generally, I would say you need to have them open to do a full commission. So we tend to leave that down to the commissioning agents to ensure that they set them correctly.
Thank you very much. That was an insightful response. We have a last question, and mindful of time, then we'll close the panel. And if the audience have some more questions coming up later, they can address those directly to the speakers in the mail address put in the chat box. The last question is how to calculate valve authority. I think you elaborated on that before, but if you can give a high-level brief on that, just for Sharma to understand.
No problems. Basically, it would be the differential pressure across your 2-port control valve divided by your differential pressure across your circuit. Now, for a DPCV, that includes all the pipe work from your impulse tube connection through your index to your coil, through all your valves and back to the DPCV. And therefore, with the examples that you saw in that presentation, the smaller the groupings, the better the valve authority. With a PICV, it's slightly different. It's integral. It will always be as close as humanly possible to 1. So hopefully that's answered your question on that. But the calculation is basically 2-port or your DP across your control valve divided by DP across your circuit.
Thank you very much for that.
No problems.
I'll share now my screen. And this is to just wrap up the session. Thank you, everyone. Thank you, Ahmad and Mark, really, for this presentation. Have been very insightful, very instrumental for the team. I believe from the nature of the questions, quite a lot of questions, the people have enjoyed the session. They have asked the query. They have been very well responded and addressed. Thank you very much to you guys for this presentation. Thank you very much to the audience for attending this webinar today. You can follow CIBSE on LinkedIn and our social media, LinkedIn and Twitter. You can find us also in our website, www.cibse.org, and any question that you may have, please feel free to address it to uae@cibse.org. Thank you very much for your attendance today, and see you on our next CIBSE UAE webinar. Bye-bye.